Hello everybody! Welcome to a new episode of Inequality. Now today we're going to talk about Cauchy inequality. In particular is Cauchy inequality in Rn, the n-dimensional Euclidean space. We could talk about that Cauchy inequality in a general vector space, but I want to make it as high school student and first year unit student friendly. So we stick with Rn. So in Cauchy inequality, let U and V be vectors on Rn such that we write U as Ui, that means U1, Un, and V as Vi, such that V1, Vn, so it should be Vn. Then we have the following. U dot V square is less than equal than U dot, let's use that, the modulus of U times the modulus of V. So that would give us the sum of Ui, Vi, the dot product from 1 to n and all squared, less than equal to sum of Ui squared from all I to sum of Vi squared. So proof. We consider the following polynomial in X is that U1x plus V1 square all the way to UNX plus VNX, and that is clearly greater than equal than 0. So when we expand this bracket, we got U1x all square plus V1 square plus 2U1 V1x plus UNX square plus Vn square plus 2 UN Vnx, and that would give us U1 square plus all the way to UN square x square plus 2 U1 V1 to UN Vn x plus V1 square to Vn square. That gives us Ui square to xn to 2 Ui Vi x plus Vi square. Since this is quadratic polynomial, quadratic polynomial sorry, I mean non-negative. Non-negative quadratic polynomial, then it has at most one root. For example, it could be the case with just touching the x-axis, or is completely above the x-axis. So we have at most one root. So that means is discriminant is less than or equal to 0. Now, so just quickly compute that discriminant formulas for quadratic is delta equal to b squared minus 4ac, and b squared, b is equal to 2 sum of ui vi, so it's 2 of sum of ui vi all square minus 4 times a is the sum of ui square times c, and c is sum of vi square, and that gives us 4 times sum of ui vi square minus 4 times ui square times vi square, and that is less or equal than 0. Therefore, we got ui vi sum of that all square minus ui vi square is less than or equal than 0. Therefore, we got ui vi all square less than or equal than ui square times vi square, and this is exactly what u dot v all square, consider their vector, that's the modulus of u times modulus of v. And next we look at an application with a typical application for is application is triangle inequality in Rn. So we just quickly record a triangle inequality if given a triangle in two-dimensional space, the length xy, and that is set. We got x plus y is always greater or equal than z. So in Rn, but now we're looking at some arbitrary n-dimensional instead of just two-dimensional. So let p equal to xi, x1 to xn, and q equal to yi, y1 to yn be two arbitrary points arbitrary points on the Euclidean space Rn, then the distance PQ is equal to QP is equal to x1 minus y1 square plus xn minus yn square, and square root of that is equal to sum of xi minus yi square, and taking the square root of that, and for any 3 points PQR in Rn, the triangle inequality holds. That is, PQ is less equal than PR plus RQ. So proof. So we first consider R is the origin O equal to or 0, and then PQ square is equal to sum of xi minus yi square, sum of all I is equal to, we expand the bracket, sum of xi square plus yi square minus 2xi yi, and that is equal to, that is bracket, so sum of xi square plus sum of yi square minus sum of xi yi, put the 2 outside, and that is less and equal than sum of xi, sum of yi plus 2 times sum of absolute value of xi yi. Now we need to rewrite that a little bit. Rewrite to sum of I xi yi equal to 2 of sum of xi yi's absolute value of that all square, and then taking the square root, and then by Cauchy inequality we just proved, we got that is less than sum of xi square times sum of yi square and square root of that. Therefore, hang on, aside a little bit, so just don't want to confuse us, and that is less than equal than sum of xi square plus yi square plus 2 times sum of xi square times yi square, the square root. And that is by triangle inequality. That bit is, sorry, not by Cauchy inequality. This particular step here. So, and we observe that is equal to square root of sum of xi square and all square plus square root of sum of yi square all square plus 2 times square root of xi square. Hang on. Keep forgetting the sum of xi square times sum of yi square, square root of that. And that is a quadratic formula. We got that square root of sum of xi square plus square root of yi square and all square. And since the distance of PO is indeed equal to sum of xi square and taking the square root, so that should be PO, and OQ is equal to square root of sum of yi square. So that is equal to PO plus OQ all squared. Therefore, we have PQ squared is less than PO plus OQ all squared. Therefore, we got PQ is less equal than PO plus OQ. Now let's consider the general case. In general case, I is equal to some arbitrary point, set I, where set 1 all the way to set n, and let P dash equal to xi minus set I, and Q dash equal to yi minus set I. Therefore, we got PQ is equal to what we got, sum of xi minus yi all square, taking the square of that, is equal to sum of xi minus set I plus set I minus yi all square. And don't forget the square root. That is equal to sum of xi minus set I minus yi minus yi minus set I. That all square, and taking the square root of that. And keep that in mind, this xi minus set I is P dash. And yi minus set I is Q dash. So that is actually the distance of P dash and Q dash. And also, we can claim that PR is equal to P dash O and RQ is equal to OQ dash. Hence, the general case is reduced to the first case. Okay, that's all I got for today. Thank you for listening, and I see you next time. Bye bye.